Welcome to another What's Up video, where we explore different system installations in industrial settings. This episode covers an introductory overview into the design, installation, integration, and commissioning of emergency voice communication systems for onshore and offshore applications. Emergencies can strike at any moment, and in critical industries like oil and gas, petrochemical plants, and offshore platforms, reliable communication is vital for safety and fast response. The first part is system design. Designing an emergency voice communication system starts with understanding the unique environment and its specific requirements. Offshore facilities like oil platforms and FPSOs face challenges such as harsh weather conditions, high humidity, and explosive atmospheres, while onshore sites may need to cover vast industrial zones. Let's break down the key components of an EVC system in more detail. Control unit or master control panel. This is the core of the EVC system, located in the central control room. It manages all voice communications across the facility, monitoring the system's status, coordinating communication zones, and managing emergency calls. Some features include touchscreen interface for easy operation and monitoring, status indicators, real-time monitoring of line conditions, battery status, and alarms. Emergency call prioritization. Ability to prioritize certain calls during emergencies to ensure critical information is transmitted first. Network interface. Allows for integration with other systems like the public address, general alarm system, or fire detection systems. Next, we have emergency call points or field stations. These are strategically placed throughout the facility to allow personnel to initiate communication in case of an emergency. They come in various forms depending on the location and hazards present. For example, wall-mounted handset units. These stations typically have a push-to-talk handset and are mounted in key locations such as escape routes, muster points, or hazardous areas. Then we have explosion-proof stations for use in hazardous environments. These stations are ATEX or IECEX certified to prevent ignition in explosive atmospheres. We also have hands-free units, since some environments may use hands-free stations with robust microphones and speakers, allowing users to communicate without needing to pick up a handset. Common features are push-button activation, immediate call initiation by pressing an emergency button, visual indicators, LED indicators for power, active calls, and fault conditions, durability, waterproof, dustproof, and corrosion-resistant for harsh environments. Another important function is amplifiers and speakers. The amplifiers boost the audio signal to ensure that the voice communication is audible in large or noisy areas, while speakers are used to broadcast the voice messages or alarms. Components include amplifiers, which are located in control rooms or distributed throughout the facility. These increase the power of audio signals for clear communication over long distances or in large spaces. Speakers, which are installed throughout the facility, especially in high-noise areas like process plants or machinery zones. Explosion-proof versions are used in hazardous locations. Common features include high sound pressure levels, SPL, designed to cut through background noise in industrial environments. Directional or omnidirectional. Depending on the area, speakers can focus sound in a particular direction or broadcast 360 degrees. Cabling infrastructure forms the backbone of the EVC system, connecting all the components together and ensuring that communication signals can flow uninterrupted. This includes fiber optic cables, which are often used for long-distance connections and in areas where electromagnetic interference, EMI, is an issue, and copper cables, twisted pair or coaxial, which are suitable for shorter distances or non-critical areas. Some considerations are an explosion-proof conduit. Since in hazardous areas, cables are often routed through explosion-proof conduits, and redundancy, as redundant cabling paths and loops ensure that communication is maintained even if a section of cable is damaged. The power supply units ensure continuous operation of the EVC system, even in the event of a primary power failure. Backup battery systems provide uninterrupted power in case of a power outage, ensuring that the system remains operational during emergencies. The EVC system integrates with the PA/GA system to ensure that emergency messages can be broadcasted to all personnel across the facility. In many cases, the EVC system can trigger automatic PA announcements during an emergency. Automatic message triggering is when a pre-recorded emergency messages can be activated if an emergency is detected by the EVC system. During an emergency, the EVC messages take priority over standard announcements to ensure that critical instructions reach everyone promptly. Zone management allows for broadcasting to specific zones or the entire facility, depending on the nature of the emergency. Monitoring and alarm systems continuously monitor the health of the entire EVC system, generating alerts for faults, power failures, or line issues. This ensures that any issues are identified and resolved before they can impact system performance. Software interface and system configuration is used to configure the EVC system during commissioning and to monitor system health during operation. It allows the customization of communication zones, call priorities, and system responses to different emergency scenarios. In many facilities, the EVC system needs to connect with external communication systems such as landline telephones, mobile networks, or satellite communication for contacting emergency services or coordinating with other facilities. These components work together to provide a robust, reliable, and efficient emergency communication network that can operate in the most demanding onshore and offshore environments. The design of the system emphasizes redundancy, resilience, and compliance with international safety standards to ensure that critical communication is always possible during an emergency. Next up is the installation process. Once the design is finalized, the installation phase begins. This requires meticulous planning and coordination with various teams, including electrical, mechanical, and network engineers. For offshore environments, compliance with international standards like IEC 60079 for explosion-proof installations is mandatory. Certified equipment is installed to withstand these challenging conditions. Onshore installations also focus on durability and reliability but can benefit from less stringent requirements in non-hazardous areas. Proper cable routing, terminations, and mounting of field stations are crucial. The installation team ensures that all connections are secure, protected from environmental damage, and accessible for maintenance. Commissioning and testing. Commissioning is the final phase where the system is tested in real-world conditions. Technicians perform a variety of tests, including audio clarity testing, verifying that communication is clear and audible across all stations. Alarm integration testing, ensuring that the system automatically interfaces with alarms and other emergency signals. Failover testing, simulating network failures to test redundancy and system resilience. The system is tested against simulated emergency scenarios to confirm that it works flawlessly under pressure, meeting all regulatory standards, such as the NFPA 72 and N60849 for safety communication systems. Designing, installing, integrating, and commissioning an emergency voice communication system is an intricate process that requires careful planning and expert execution. Whether onshore or offshore, these systems ensure that in the event of an emergency, clear and reliable communication is always available, saving lives and minimizing risk.